Chapter 26, we've been doing hypothesis testing, and so now we're going to do a new hypothesis test, which is the t-test for averages. So first we're going to talk a little bit about the difference between a population SD and a sample SD. Remember, SD stands for standard deviation. So the formula for the standard deviation of a population is that SD equals the first observation minus the average squared plus the second observation minus the average squared plus all the way up to the last observation minus the average squared divided by the number of measurements you had. So that's how you find the standard deviation for a population. But the formula for the standard deviation of a sample is almost the same, except for instead of dividing by the number of measurements, you divide by the number of measurements minus 1. And our textbook calls this SD plus instead of just SD. Most other textbooks use the symbols sigma versus S if you've taken another textbook. Otherwise, don't worry about it. And why would we do it this way? Why do we change our formulas? And the reason why, statisticians have figured out if they use that formula with the minus 1 instead, when they have their sample standard deviation, that their results are less biased. Now, there's technically a conversion formula you could do. So you take your population SD and times it by the square root of number of measurements over number of measurements minus 1. But we're not going to worry about doing that in this class. Instead, in this class, I'll tell you if it's a population SD or a sample SD. And if it's a sample SD, the conversion will have already been done for you. And the reason why is I just have the calculator calculate the sample SD for me in the first place, since it knows how to do that. But then we get to what we truly care about, which is right here. So when we use the sample standard deviation, we have to estimate the population standard deviation with our sample standard deviation, in addition to estimating the population average. And this just adds extra error and uncertainty to our problem. So we have to compensate for that extra error by using the t-curve instead of the normal curve. And we haven't talked about the t-curve yet. Let's talk about the t-curve. The t-curve is similar to the standard normal curve, but it has one extra property, which is called degrees of freedom. So here's a few descriptions of pictures for the t-curve. So this first one, you have your solid black line, and that's the t-curve with 1 degree of freedom. And then I also put in this dashed line, overlaid it with the normal curve. So the dashed line is the normal curve, the solid line is the t distribution. Notice that there's a bit of a difference here between the two curves. The t-curve has a lot more area in the tails. The tails are a little bit fatter. But when I go to 10 degrees of freedom for t, notice by the time I get to 10 degrees of freedom, it's hard to tell the difference between the t-curve and the normal curve. And when I get to 30 degrees of freedom, the t-curve and the normal curve overlay almost exactly. So we can hardly tell the difference between the z for normal and the t-curves. And the reason why is as your degrees of freedom get bigger, the t-curve gets closer and closer to the normal curve. Just a few things, the t-curve is symmetric and it's always centered at 0. So it's the t-curve is similar to the standard normal curve. Z. So remember, there's lots and lots of normal curves with different means and standard deviations, but the standard normal curve has a mean of 0 and a standard deviation of 1. And the t-curve is very similar to that standard normal curve. So what we're going to do is we're going to use the t-table to find these areas. This t-table is very similar to the one in your textbook. Now I know in the z-table it always gave us areas to the left. Now for some reason, traditionally, the z table always gives us areas to the left, but the t table always gives us areas to the right. Okay, I don't know why they came up with that tradition and made them separate, but they did. Now we get to deal with it. Okay, so once again, it will always give us areas to the right. Now the t table is set up very differently from the normal table. In the t table, the actual t values are inside the table. So inside the table, those are our t values, whereas the areas are along the top of the table. So notice it doesn't give us that many areas. There's only a few areas that it actually gives us. The degrees of freedom are down the left side of the table. Now, if the degree of freedom you want isn't on the table, because once we get to like 30, we start skipping some. So if the degrees of freedom you want aren't on the table, then you just round down for your degrees of freedom. Notice at the very end, you do have a row called normal, and that's because as your degrees of freedom get bigger and bigger, you get closer and closer to the normal table. And so once you pass 1,000, you get to about the normal distribution. So using this t table, we want to find the area to the right of t equals 1.81 with 10 degrees of freedom. So what I do is I come and I find 10 degrees of freedom, and I look for t equals 1.81, and the t table always gives me areas to the right, so the area to the right is 5%. So my answer is 5%. Now, to the left of 1.81, so here's t equals 1.81, we want the area to the left. Now, my t table doesn't give me areas to the left, but I can use the complement rule, so the area to the right was 5%, so this would be 100% minus 5%, which is 95%. So my answer is 95%. Now my next one, I want to find the area to the left of t equals negative 1.81. Now this is an issue because if I go to my t table, it doesn't give me any areas to the left. But also notice if you look at the t values inside the table, they're all positive. There are no negative values. So anytime you're interested in negative, you have to use symmetry. Specifically, if you look at number 1, we found the area to the right of 1.81. That will be the same as the area to the left of negative 1.81. And so you have the symmetry here between these two problems. So it's 5% up here, then it's 5% here. Okay, my next one, we want the area between 0.72 and 1.44. So here's my 0.72, here's my 1.44. We want the area in between, and now we have 6 degrees of freedom. So let's go back to our t table. Now we have 6 degrees of freedom, and we wanted the area between 0.72 and 1.44. Which means that we have two percentages, 25% and 10%, and we're going to subtract them just like we did before with the normal table. So 25% minus 10% equals 15%. So we want the area in between two numbers, you have to subtract the two areas. Okay, now still with 6 degrees of freedom, look for the area to the right of t equals 3. So we have 6 degrees of freedom, we're looking for t equals 3. And so we're at 2.45, 3.14, 3.71, but 3 itself is not on there. So 3 would be somewhere between 2.45 and 3.14. Which means that the area is somewhere between 2.15 and 1%. And that will actually be our final answer. we'll say it's between 1% and 2.5%. We don't try and figure out exactly what it is. If we really wanted to, we could use a calculator. But as far as the purposes for this class, you could just say, okay, it's between 1 and 2.5%. And the area to the left of negative 2.5, so here's my negative 2.5. I'm looking for the area to the left. Now there's a problem. There's no negative values on my table, and there's also no areas to the left. But this area would be the same as if I draw my curve and I do t equals positive 2.5 and look for the area to the right. Those two areas would be the same due to symmetry. So let's go to our t table. We have 4 degrees of freedom and we're looking for 2.5. So 4 degrees of freedom, look for 2.5, it would be somewhere about here. So the area is somewhere between 5 and 2.5%. So this is between 2.5 and 5%. So this area is between 2.5 and 5%. It is frustrating that we can't narrow it down any better than that with the table, but that's the way things are, and we just leave that as our final answer. Now let's talk officially about the t-test for the average. So we use this test if we're interested in the population average, but we do not know the population SD. Instead, we have to estimate it with our sample standard deviation. Okay, so we learned about the z-test, and we use the z-test if we know the population standard deviation. We use the t-test if we know the sample standard deviation. Now, which one is going to come up more common in real life? Well, in real life, we don't know the population standard deviation very often. Sometimes there might be situations where we do, but usually we don't know the population standard deviation. So the t-test is actually much more common in real life. And then you have this assumption that you will have to check is you can only use the t-test if the data is normally distributed or the sample size is at least 30. The test statistic is t equals our sample average minus expected value over standard error. So exactly the same as for our z-test, but now we're just going to call it t. And the new thing about the t-test is you also have to have degrees of freedom. And your degrees of freedom is equal to your sample size minus 1. And, of course, you have to use the t table instead of the z table. The expected value for the average is still going to be our population average, and we don't know for sure what the population average is, but for our calculations, we assume that the null hypothesis is true. So whatever number you have in your null hypothesis, that's what we're saying is our population average. And then the standard error is supposed to be your population SD over the square root of the sample size. But we don't know the population SD, so instead we use the sample standard deviation over the square root of the sample size. Now technically, if your sample size is bigger than 25 or so, you could just use the z-test because the final results will be almost identical. However, this is almost never done in the real world because in the real world we use software, and software can easily find the exact p-value for any degrees of freedom for the t-test. And so since I've never seen people use the z-test in real life just because it's a big sample size, I don't want to teach you that in this class either. So in this class, you should always use the t-test if the t-test is appropriate, meaning that you know the sample SD, since that's how you decide to use the t-test. So let's practice deciding if we should use the z-test or the t-test. So number 1, experimenters measure how long it takes for a mouse to get through a maze. The average time is 15 seconds. 40 mice are given a shot of steroids and timed again. The average time is 12 seconds with a sample standard deviation of 2 seconds. Sample standard deviation. So because we have the sample SD of 2 seconds, because it's a sample SD, we're going to have to use the t-test. And finally, is there evidence that the mice with the steroid are faster? So if they're faster, because it's talking about the average time it takes to go through, if you want them to be faster, that actually means less time. So our alternative hypothesis will be that there's less time, which means for less, we would find our t-value and shade to the left. So this will be a left tail. Now number 2, the Census Bureau reports that households spend an average of 31% of their total spending on housing. Residents of Logan wonder if this is true for their area. They interview a sample of 15 households and find that on average 29% of their income goes to housing. If the Logan residents know that the SD for the area is 4%, is there evidence that the Logan average is different from the national average? So on this one, when you look at it, it says it's the SD for the area. They didn't talk about it being the SD for just their sample. They said it's the SD for the entire area. So that would be a population SD. So we'd have to use the z-test. And let's just see what area we're going to shade. So is there evidence that the Logan average is different from the national average? They didn't say if they think it's higher or lower. So you're going to find your z-value and shade both tails. Number 3, you purchase a shipment of 9-volt batteries. You measure the voltage of a random sample of 60 batteries and find that the average voltage is 9.1 with SD equals 0.2. Now, it didn't specifically say sample SD or population SD, but if you read the statement, we measure the sample and find that the average is this with the standard deviation of that. To me, when I read that, it sounds like that's the standard deviation for that specific sample it's telling me about. So this would be our sample standard deviation. So we'd have to use the t-test. Now, is the average for the shipment different from the nominal voltage? So it just said different from, it didn't say if it thinks it's higher or lower. So we're going to have to shade both tails. Now let's actually try some t-tests. In example 265, an English exam is taken by 2,000 students. The exam scores are known to follow the normal curve. The teacher says that the population average of all 2,000 scores is 75, but one of the students thinks that the population average is actually lower. So she takes a simple random sample of 9 students. So my sample size equals 9. And she found that they got these scores, so 65 or 63, 53, set it up to 92. The sample average is 66.6. So my sample average, the sample standard deviation. So my sample SD equals 18.4. Test to determine whether the population average really is 75 or if the student is correct. So we're comparing to 75. Let's see what else. Oh, exam scores are known to follow the normal curve. So it follows the normal curve, which is good because we have a small sample. My sample is only 9. And so if it didn't follow the normal curve, I couldn't do this problem. So because I have a sample SD, I know I have to use the t-test. For my null hypothesis, it'll be that my population average is, so what are we comparing it to? We're comparing to see if it's really 75. So the status quo, nothing interesting, would be that it is 75. The alternative is that my population average is, let's see, we want to see if the student is correct. This student thinks that the population average is actually lower. So we would test if it's less than 75. Now let's calculate our test statistics. So the expected value for the average would be 75 because we assume that the null hypothesis is true, so the population average would be 75. And the standard error is population SD, but we don't know that, so we'll estimate it with our sample SD over square root of the sample size. So my sample SD is 18.4. My sample size is 9. This gives me 6.13. Now let's actually calculate my test statistics. So T equals my sample average minus the expected value for the average over the standard error for the average. My sample average was 66.6. I expected 75, and the standard error is 6.13. So this gives me negative 1.37. Now you need to know degrees of freedom. Degrees of freedom is sample size minus 1. My sample size was 9, so 9 minus 1 is 8. And for my p-value, so here's t equals negative 1.37, and I'm looking for the area to the left because we're testing that the average is less than 75. How will I actually find that? Remember, that's technically the same as positive 1.37 and shade to the right. So let's go to the t-table, look up 1.37 with 8 degrees of freedom. So 8 degrees of freedom, 1.37, that would be here-ish. So my probability is between 25 and 10%, closer to the 10%, but somewhere between 10 and 25%. So my p-value is between 10% and 25%. Now for my conclusion, we don't know exactly what the p-value is, but no matter where it is between 10 and 25%, it's bigger than 5%. So this is a big p-value, specifically bigger than 5%. So because it's a big p-value, we will fail to reject the null hypothesis. And when we fail to reject the null hypothesis, remember, we still have to word our conclusion in terms of the alternative hypothesis. So we wanted to know if the population average was less than 75, but we couldn't reject the null. We failed to reject the null, and so we say that we don't have enough evidence to say that the population average is less than 75. Maybe it is, but we don't actually have enough evidence to conclude that and feel pretty good about the conclusion. So example 266, tomatoes of a certain quality are supposed to have an average weight of 5 ounces. So I'm guessing that we are going to compare to 5, but well, you should probably keep reading. I'm a little skeptical. I think that the average is somewhere greater than 5 ounces. So my question is, I'm going to ask, is it greater than 5? That's the question we're interested in. Let's see, I select 10 tomatoes at random. So if I select 10 tomatoes at random, that means my sample size equals 10. Let's see, the average weight of these 10 tomatoes is 5.79, so that would be my sample average because it's for those specific 10 tomatoes. And a sample standard deviation of 0.91 ounces. Is there evidence that the average weight of this type of tomato is greater than 5 ounces? So once again, we're comparing it to 5. Specifically, I want to know, is it greater than 5? The null hypothesis then would be that the average weight of all tomatoes of this type is 5 ounces. The alternative is that the average of all the tomatoes is greater than 5 ounces. So you have to either say the average of all, or you have to say the words population average, so I know that you're talking about the population. Then for your test statistic, first we calculate the expected value and standard error. So for the expected value, we assume that the null is true, which means that my population average would be 5. For the standard error, we don't know the population SD, so we have to estimate it with the sample SD over the square root of our sample size. My sample SD is 0.91. My sample size is 10. So this gives me 0.29. And T equals my sample average minus the expected value for the average over the standard error for the average. My sample average was 5.79 minus 5 over 0.29, which gives me 2.72. So that's my test statistic T. Now for degrees of freedom, it's your sample size minus 1, so 10 minus 1, which gives me 9. So that's my degrees of freedom. Now for your p-value, here's our test statistic of T equals 2.72. And we're going to shade to the right because our alternative hypothesis was that the average is greater than 5 ounces. So shade to the right. So 9 degrees of freedom, 2.72. 2.72 would be somewhere about here, between 2.26 and 2.82. So the probability is somewhere between 1 and 2.5%. So my p-value is between 2.5 and 1%. Now for your conclusion, we don't know exactly what the p-value is, but our p-value is smaller than 5%, so it counts as a small p-value. So we will reject the null hypothesis. This means that we found evidence that the average of all the tomatoes is greater than 5 ounces. In our next example, a health textbook claims that the average weight of adult males is 72.6 kilograms. You think that the average weight in your town might be different, so you take a simple random sample of 20 men. So my sample size equals 20. Let's see. The average weight, so that would be the sample average because it's talking about the men in your sample, is 90 kilograms. And a standard deviation of 17. Now, it didn't say if that's a sample or population SD, but it's in the same sentence. It's talking about the average weight in our town. The simple random sample of 20 men, their average weight is 90, their standard deviation is 17. So I would say that was a sample SD equals 17. So because that's a sample SD, we have to use the t-test. And what are we comparing it to? So we think our town might be different from everywhere else. The health textbooks claims that the average is 72.6, so we're going to compare to 72.6. Conduct a hypothesis test. Notice that everything is blank, so we get to try and remember the steps ourselves. So the null hypothesis would be that the population average for our town is 72.6. The alternative is that the population average for our town is, let's see, do we want it greater than 72.6, less than, or just not equal to? It just says it might be different. It doesn't say greater than or less than, so we'll just say is not 72.6. Now let's do our calculations to find our test statistics. So let's find the expected value of the average, which it should be 72.6, and the standard error for the average. You do the SD over square root of the sample size, so 3.8. And then your test statistic T is your sample average minus the expected value for the average over the standard error for the average. My sample average was 90, but I'd expected 72.6, and the standard error is 3.8. So this gives me 4.58. And the degrees of freedom is your sample size minus 1, which is 20 minus 1, so 19. So here is my 4.58, but because our alternative hypothesis is just that our population average is not 72.6, we have to look at both tails. So we'll look at the symmetry. We'll find the area to the left of negative 4.58 and the area to the right of positive 4.58. So let's go to our t-table. 19 degrees of freedom, 4.58. (19) 4.58 isn't on there. It's going to be somewhere way off the charts, which means that the probability is somewhere off the charts. It's actually going to be pretty small, but all I can say for sure is that it's less than 0.5%. So this area is less than 0.5%, and this area is less than 0.5%. So my total p-value is less than 1%. To get that, I just did 0.5 plus 0.5 equals 1. So I don't know exactly what my p-value is, but my p-value is less than 5%. So it is a small p-value. Whenever we get a small p-value, we reject the null hypothesis. And because we rejected the null hypothesis, we have evidence that the average is not 72.6. Actually, let's be a little more specific. We have evidence that the average weight of all adult males in our town is not 72.6 kilograms. Since it's a real world conclusion, you should add a little bit of context into it. But notice that's all that we say. We just say it's not 72.6. We don't say if it's higher or lower, just that it's not 72.6. And that's what this little note at the bottom of the page is talking about. So when you do a two-tailed test, unfortunately all you can say is whether or not the population average is 72.6. We can't actually say if it's higher or lower based on the hypothesis test alone. You could use a little bit of logic to maybe figure it out, but as far as the hypothesis test, all it tells you is that the weight is not 72.6 kilograms. And at this point, we're going to summarize some of our hypothesis tests, so not just the t-test, this is for all the hypothesis tests. So first is that our null hypothesis is the status quo or default hypothesis, so nothing interesting. And you have to have strong sample evidence that the null is false before you reject it. Kind of, again, that innocent until proven guilty, or you have to be beyond reasonable doubt. You have to have very strong evidence before you reject the null hypothesis. When you calculate the test statistic, we assume that the null hypothesis is true. Now, the further our actual observed data is from what we expect, the more evidence we have against the null hypothesis. The p-value, it's always good to know the interpretation of the p-value. The p-value is the chance of getting a sample value, or your test statistic, depending on what you want to talk about, at least as weird, meaning extreme, as the one we got if the null hypothesis were true. So big if there. Now, the smaller the p-value, the less likely we are to believe the null hypothesis is plausible. So this is very important too. So the smaller the p-value, the more evidence we have against the null hypothesis. So then the smaller the p-value, the more evidence we have for the alternative hypothesis. Just remember, we said that the p-value is not the chance that the null hypothesis is true. The p-value has that long, involved definition from up above, and that's the only definition of the p-value that works. So the p-value is a chance of us seeing data as far away as what we saw if the null hypothesis were true. So if the p-value is small, we tend to believe that the null is false. Now, we reject the null hypothesis if the p-value is small, so that's something you should know as well. Less than 5% we say statistically significant, less than 1% would be highly statistically significant. And don't forget that you write your conclusion in the real-world context of the problem, and it's always in terms of the alternative hypothesis. So we reject the null hypothesis and etc., or we fail to reject and etc. When the data is too far from the predictions of our theory, that's bad for our theory, so people start to disbelieve in the theory. In statistics, the null hypothesis is rejected when the observed value is too many standard errors away from the expected value. Now just keep in mind, lack of significance, having a big p-value, failing to reject the null hypothesis, doesn't actually imply that the null hypothesis is true, just that we didn't find any evidence against it. And a significant result, a small p-value, does not mean that we've proved the alternative hypothesis is true either. It just means we have evidence for the alternative. And due to convention, if our evidence isn't strong enough to convince us to reject the null hypothesis, we do not say we accept the null. Instead, we say we fail to reject the null, or we don't have sufficient evidence to reject the null. And finally, statistical significance does not always mean practical significance. Remember, statistical significance means we're very sure, statistically speaking, that there's a real difference here. Practical significance means would that difference actually matter in real life?